In this presentations, we are going to discuss about threads in OS, where the outline is multi-core programming, multi-threading models, thread libraries, threading issues, operating systems examples, and deadlocks. The objectives are identify the basic components of a thread and contrast threads and process. Then describe the benefits and challenges of designing multi-threads applications. Then describe how the Windows and Linux operating system represent threads. In the single and multi-threaded process, a single thread is used to execute the particular program or process. In this multi-thread process, more than one threads are used to execute the process. Actually, the thread is an execution unit. So each execution unit is perform different operations in the multi-thread process. The multi-threaded server architectures, the client sent a request to the server. The server accept the request from the client and create a new thread to service the request. Then resuming listening for additional client request. Then that created thread is passed to the process to the executions. The benefits are responsiveness, resource sharing, economy, scalability. In this multi-core programming, a multi-core or multi-processor systems puts pressure on programmers. Challenges includes dividing activities, balance, data splitting, data dependency, testing and debugging. Then in the parallelism, it implies the systems can perform more than one task simultaneously. At the same time, it also performs the concurrency supports more than one task making process. So here the single processor core scheduler providing concurrency occurs. In this concurrency versus parallelisms, a single core it occupy the time or manage the time utilization for perform the particular process by the subdivisions of T1, T2, T3, T4 for the single process. Then the next process take the time T1, T2, T3, T4. It's a single core processing. In this parallelism, each process can parallelly executed. So in this core 1, execute the first task in the time schedule T1. At the same time, core 2 the second task in the time schedule T2. So afterwards, the core 1 executes the third task of the first process, that's in T3. Then the second core executes the final process in T4. So here the parallelly process to be done for the time saving. So in this multi-core programming, types of parallelisms are data parallelism and task parallelisms. Distributes subsets of the same data across the multiple cores, same operations on each. That's in data parallelism. The task parallelism distributed threads across the cores, each thread performing unique operations. The descriptions about the data and task parallelism. So in this data parallelisms, each individual data are given to the individual core, but in the task parallelism, the same data are shared by the 4 tasks. User threads and kernel threads. User threads managements done by the user level threads library. 3 primary threads libraries. POSIX thread, pthreads, then Windows thread, Java thread. In the kernel threads is supported by the kernel. Example, virtually all general purpose operating systems including Windows, Linux, Mac OS X, ISS, then Android. So the user and kernel threads. So in this user space has the user thread, the kernel space has the kernel threads. So in this multi-threading mode are many to one, one to one, many to many. So in this many to one, many user level threads mapped to single kernel threads. So one thread blocking causes all to block. So multiple threads may not run in parallel on multi-core systems because only one may be in kernel at a time. Few systems currently use this model. So in this many to one model, one kernel threads are available, many user threads are available. So all the user threads are run in a one kernel threads. In this one to one, each user level thread maps to kernel thread. That is, in creating a user level thread creates a kernel thread. So here each user level threads are connected to the kernel level thread. So each are connected separately. So here the number of threads per process sometimes restricted due to the overhead. This is a disadvantage. So in this many to many model allows many user level threads to be mapped to many kernel threads. So allows the operating systems to create a sufficient number of kernel threads. So two level model. In this two level model, it isn't similar to the many to many. So expect that it allow a user thread to a bounded that's in kernel threads. Then single handling. So here signal are used in the Unix systems to notify a process that a event has occurred. A signal handler is used to process signals. Signals is generated by a particular event. A signal is delivered to a process. A signal is handled by one of two signal handler, that is a default and user defined. Every signal has default handler that kernel runs when the handling signals. So here the user defined signal handler can override the default for single threaded single delivered to process. So where should a signal be delivered for multi-threaded? So they deliver the signal to the thread to which a signal applies. Delivers the signals to every thread in a process. So deliver the signal to certain threads in the process. Assigns a specific thread to receive all signals of the process. So the thread challenges or issues. The terminating a thread before it has finished isn't major issue. So thread to be cancelled is target thread. Two general approaches: asynchronous cancellations and difference calculations. So in this deferred calculations allows the target thread to periodically check if it should be cancelled. In this asynchronous cancellations terminates the target thread immediately. So is encoding for the how to cancel the thread. Then the operating system examples are Windows thread and Linux thread. So in this Windows thread, the Windows application program interface, that is a primary interface for the Windows application. So it implements the one-to-one mapping kernel level. Each thread contains a thread ID register set representing state of processor, separate user and kernel stacks for when the thread run in user mode or kernel mode, private data storage area used by runtime libraries and dynamic link libraries. The register set stacks and private storage area are known as the context of the thread. So in this descriptions, the kernel space and user space have the thread structure. So in this E thread and K thread is available in the kernel space. So it has a pointer to the next thread. So in this K thread it has a scheduling and synchronizations informations. So from this it has linked to the user space thread. So in this Linux thread, Linux refers to them as a task rather than the threads. Thread creations is done through the clone system call. Clone allows a child task to share the address space of the parent task. So in this deadlock characterizations, deadlock can arise if four conditions hold simultaneously. The first one is mutual exclusions, hold and wait conditions, and no permission and circular wait. So the methods for handling the deadlocks are ensure that the systems will never enter a deadlock state. So in this deadlock preventions and deadlock avoidance. So they allow the systems to enter a deadlock state and then recover. So at the same time ignore the problems and pretend that deadlocks never occurs in the system. So that preventions are mutual exclusions and hold and wait. These two kind of process used to prevent the deadlocks. So that and the no preemptions and circular wait. So in this, if the process that is holding some resource requires another resource that cannot be immediately allocated to it, then it resource currently being held or released. Deadlock avoidance. The simplest and most useful model requires that each thread declare the maximum number of resources of each type that it may need. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait conditions. Resource allocation state is defined by the number of available and allocated resources and the maximum demands of the process. So in this deductions, states and the algorithm and recovery schemes are mainly important. So in this avoidance is maintained by the resource allocations and the maximum numbers of the resource is utilized. At the same time the deductions is also, then the deductions algorithm is described by the work and finish vectors. So it is of length m and n. So the work is available for I equal to 1 to n. If allocations is not equal to 0, then finish is equal to false. Otherwise finish is equal to true. And find an index I such that both finish of that process is equal to false. Requires the work is less than, that is an proper conditions. So the process terminations in the recovery from the deadlock. Abort or deadlock threads abort one program at a time until the deadlock cycle is eliminated. In which order should be choose to abort? Priority of the thread, how long has the thread computed and how much longer to completion. Resources that the thread has used, resources that the thread need to complete, how many threads will need to terminate as the thread interactive or batch. So in this resource preemption has selecting a victim and roll back and starvation. Thank you.